So acids and bases, right? First of all, they both conduct electricity. Spoiler alert, they're both electrolytes. Acids have a sour taste, which is why they're a lot of foods, tomato juice, lemons, things like that. Bases taste bitter. If your mom washes your mouth out with soap, that's because soap is a base and it tastes really bitter. If you've ever tasted baking soda by itself, it's one of the most bitter things you'll ever taste. And baking soda is obviously edible because we use it for baking. And it also is used as an antacid. So it's used as a medicine. It's not a very good antacid. Acids turn litmus paper red, bases turn litmus paper blue. You don't need to know what litmus is right now, but what I do want to tell you is that there are acid base indicators. So there are certain chemicals that you can add to things to tell you whether it's an acid or a base. Acids react with metals to form H2 gas. This is why you should not clean stainless steel with a vinegar solution because you don't want the acid to be on the metal. Bases feel slippery. Soaps, detergents are bases. And then here's some examples of acids, and here's some examples of bases, right? We've got a lot of foods here because they have that good sour taste. Bases, antacids is a type of a base that's like an anti-acid. You send it down when you're getting a stomach ache and that stomach acid is gurgling around. So you send that base down to neutralize it, all right? Also, soaps and detergents are bases. So acids and bases have been used for centuries. They've been talking about them a long time. Um, Different people in the past have used different definitions of acids and bases. And when you get into higher level chemistry like AP, you will learn up to like 4 different definitions for what it means to be an acid or a base that's kind of evolved throughout time. But we're going to focus on a really easy definition. But before we can even talk about it, you have to understand this principle, okay? Water, pure water, when it's just sitting there in a cup, will break apart a little bit into hydrogen ions and hydroxide ions. So water breaks apart a small degree like that. And I'm going to write down those names because these names are going to become kind of confusing here in a minute. So water breaks apart into hydrogen ions, and this guy is called a hydroxide. It's a good word to know for chemistry because we use it a lot in chemistry and organic chemistry. Now, not very much, okay? So water is what we call in equilibrium with the hydrogen ions and the hydroxide ions. I'm going to give you the why. This is really for if you want to explore this more, if you're going to AP. You don't need to know this for my class. But since that reaction is in equilibrium, we can determine something called the Keq value. Now, we didn't learn Keq, but you can find a lot of videos about this and learn more on your own time if you want to. I can send you in the right direction. So basically, 1.0 times 10 to the negative 14th is what we call water's ionization constant, or its Keq. Again, the only thing that you need to pull from this is this, all right? And this is that the concentration of hydrogen ions times the concentration of hydroxide ions equals 1.0 times 10 to the negative 14th. All right, another little nitpicky thing, if you ever see this symbol, those brackets, that does mean concentration. Concentration. And that concentration is, again, usually in molarity or moles over liters. So here's an example of how you use this equation. It says, find the hydroxide ion concentration. Remember, this is hydroxide ions of a solution of hydrochloric acid that has a hydrogen ion concentration of 3.0 times 10 to the negative 7th. So it's been a while since you've used this button on your calculator. So I want to review with you how to use the EE button, right? You're going to know things like that, right? You know that hydrogen ion concentration times hydroxide ion concentration equals 1.0 times 10 to the negative 14th. You're basically solving for X. This is algebra. You guys have been doing this a lot in my class and hopefully in math class. So you use the 1.0, all right, times 10 to the, that EE button, negative 14th, divided by 3.0 times 10 to the negative 2nd. All right. So you got to use that EE button. If you don't use it, then you're going to have to parenthesize everything that you do. And so you get an answer of 3.3333 sig figs. You only need 2 sig figs. So you get 3.3 times 10 to the negative 13th molar, or moles over liters. That's the concentration of hydroxide ions. All right. Okay, so our definition that we like to use is an acid is any substance that causes the H plus ion concentration to increase. And then a base is the opposite of that. A base is any substance that causes the OH minus concentration to increase. Acids, think hydrogen ions. Bases, think hydroxide ions. They are opposite of each other. Acids and bases, all of their math and everything is going to be the opposite. Now, here's another thing to just confuse you a little bit more, but you guys are ready for this? Hydrogen ions don't actually exist in water. All right? Water is very polar. So water picks up the hydrogen ions and becomes hydronium ions, right? So they get picked up by the water molecule to make these hydronium ions. This just says water plus hydrogen equals hydronium. So for us, in this class, hydrogen ion concentration is the exact same thing as hydronium ion concentration. And I told you those H words would get confusing. So you have hydrogen ions, which really don't exist, and they are now going to be forever known as hydronium ions in water. All acid-base chemistry happens in water. And then you have the hydroxide ions. All right, so we measure how acidic or basic something is by using the pH scale, all right? And this pH scale is based on a logarithm of H3O+. If you have not learned logs yet, that is okay. I'm going to show you how to use logs in your calculator. Log is on my calculator here where it says log with the little 10 after it. The log with the little 2 after it is something different. All right, let me show you this video and pay very close attention to what I just kind of talked about, this logarithm thing.
From the tangy bite of a piece of fruit to the caustic liquids used to clear a clogged sink, acids are a type of chemical that could be found in many different aspects of our daily lives. But what is it about acids that makes some safe to eat and others dangerous? When talking acids, we're going to be talking hydrogen. not the gas, but rather the hydrogen ion H+. This is a hydrogen atom that has lost its one and only electron. All acids produce H+ ions when dissolved in water, but it's how much H+ a specific acid can produce in water that will determine whether it can be safely eaten or not. But how do we conceptualize and measure H+ concentration? Søren Sørensen, a Danish chemist, pondered this question when he worked at the laboratories of a commercial brewery in Copenhagen. It was in 1909 that he developed a method of quantifying acidity, what is now known as the pH scale. His scale works by simply converting the concentration of hydrogen ions in a solution to a number between 0 and 14. If a chemical is acidic, then its pH will always be below a 7 on the scale. The lower the number, the higher the hydrogen ion concentration. The pH scale is a logarithmic one, meaning that 1 unit difference on the scale, say from 3 to 2, means a 10-fold difference in H+ concentration. But 0 to 7 is only half of the picture. So what about all these numbers above 7? Substances that correspond with this half of the scale are called bases, and they are the chemical opposites of acids. The 7 on the scale represents neutral pH, what would be perfectly pure water. Like acids, bases are found in chemicals that we encounter in our everyday lives. Cleaning products such as ammonia and baking soda are bases, as are some simple medicines like milk of magnesia. They're bitter to the taste and often slippery to the touch, kind of like soap. Even though bases are different than acids, they too can be strong or weak, and a strong base can be just as dangerous and corrosive as a strong acid. Chemically, the difference between acids and bases is that acids produce hydrogen ions and bases accept them. In water, acids produce H+ ions and bases produce OH- ions. In reactions between acids and bases, hydrogen ions will react with hydroxide ions to make water. This type of chemical reaction is called a neutralization reaction. Acids and bases are also very important in biochemistry. Many biological processes are sensitive to the pH of the surroundings, so controlling acidity in the body is crucial. Some biologically important molecules like amino acids have dual personalities. They're said to be amphoteric, which means that they can act as both acids and bases. An amino acid has a carboxylic acid group that can produce hydrogen ions and an amino group that can accept hydrogen ions. Acids and bases are all around us and can vary greatly in terms of their use and their nature, but they all involve hydrogen ions being passed around. Thanks for watching.
Okay, so the pH scale, like I said, you've learned it for a long time. People use it in their everyday lives. The guy that does the pool chemistry in our swimming pool uses the pH scale. What they've done is they've taken this very difficult math of things like 2.4 times 10 to the negative 13th, and they've put it on this very simple scale where you've got 0 to 14, and in the middle is 7, and it's neutral. And that's why it's a logarithmic scale. Okay? Now, again, mathematically, the pH is the negative log of the concentration of hydronium ions, which are hydrogen ions, right? That's because hydronium ions are a teeny tiny little number. And people don't want to deal with a tiny number when they're doing pool chemistry. They don't want to talk to other pool boys and say, hey, the pH in this guy's pool is 2.4 negative blah 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 blah. Like, they don't want to say that. So instead, they say the pH was 3. And that's a lot easier to talk to people about. All right. So when you do this in your calculator, you just throw that log button in and it will fix this into a number that means a little bit more. And then I'll show you what to do with the negative sign in a second. So that's the basic pH scale. You've been learning it since pretty much elementary school, and it hasn't changed. The only thing that's changed is that I'm telling you exactly what those numbers mean. Okay, the P in pH stands for the power, and the H is hydrogen. It's the power of hydrogen. It's how much hydrogen is in the substance. Now this is a picture of the pH scale, right? You've got very strong acids towards the 0 end of the pH scale. That means there's a very high hydrogen ion concentration. Battery acid, stomach acid. All right, way down at the bottom of the pH scale in the 0 range is where we have those burn your face off acids. Then we move towards neutral. Okay, now we're getting less and less hydrogen ions or hydronium ions. And then we move into the bases, where we're seeing way less hydronium ions and more hydroxide ions. When the hydrogen ions decrease towards 14, the hydroxide ions increase. And that's what that equation told us before. So you'll have to do math problems, and they're not super scary. They seem kind of scary because you have to use a calculator for sure to do them. A solution of hydrobromic acid has a hydronium ion concentration of 0.01 molar. What is its pH? Now, I know that some of you can do this one in your head because you understand logs, but I'm going to show you on a calculator because I have a lot of people that have not learned log yet. So the way that I do the pH is I just type in 0.01 and then I hit the log button after it. Some people on your calculator will have to hit the log button before. You'll have to get to know your calculator. Now you'll notice there's a negative sign there. I don't bother with it. I take it away in my head when I'm done. If you want to type in the negative log of it so you don't get the negative sign at the end, that's fine, personal preference. Then the next question is, what is the OH concentration of this? Well, we know that H plus times OH equals 1.0 times 10 to the negative 14. And we also know that I told you that H3O plus is the exact same thing as OH, or as H plus. So those are basically interchangeable. You can write down whatever you want because they are really the same thing. Okay, so you can use that equation and then just sub in the 0.01 molar, okay, times the OH, which becomes our X that we're looking for, 1.0 times 10 to the negative 14. And then I'll put that into my calculator, 1.0 times 10 to the negative 14th divided by 0.01. Okay, so I get 1 times 10 to the negative 12th. And if you want to keep your sig figs, then you should probably write 1.0 times 10 to the negative 12. Now again, there are ways of sort of doing this one in your head, and that's okay if you saw that, and it's really okay if you didn't. All right, what is the pH of a solution of HNO3, this is nitric acid, with an H3O plus concentration of 0.05 molar? Sorry, should be a subscript there. All right, we know that pH equals the negative log of H3O plus. pH equals the negative log of 0.050. So 0.050 log. All right, I'm going to ignore the negative sign. My pH is 1.3. You need to use sig figs. This number had 2 sig figs. So my answer ends up with 2 sig figs because of what I found in my calculator. Up to the corner here are really all the equations you'll ever use. Now I want to take it just one extra step because I do have some kids in here that are headed to AP and I don't want you to have never heard of this. But if you're not, you can kind of tune me out a little bit. There is something called POH. All right, so there's pH, which we've heard of, and there's the pH scale, which everybody talks about. POH is literally the opposite. It's the same thing as the pH scale, except now this time we're talking about OH instead of pH, instead of H, right? So it's the negative log of OH. And here's the kicker. Here's how they're related to each other. pH plus POH equals 14. So if you had a pH of 1.3, in order to find the POH, you would just take 14 minus 1.3. Is this acidic or basic? Bottom line, 0 to 7, acids. 7 to 14, bases. So its pH is 1.3. Its pOH is a much higher number, but it is, of course, acidic. So what is the hydronium ion concentration in a solution that has a pOH of 9.6? So this is mean, because now I've got to look at a couple of these. First, I'm going to turn this into pH, because pOH is not helpful to me. So I'm going to say, okay, pH plus pOH is 14. I'm going to sub in my pOH there and subtract. It's as simple as subtracting. Now it's got a pH of 4.4. So now this is a little bit easier to work with. Now I'm working with this equation. pH equals the negative log of H3O plus. All right, pH, negative log of H3O plus. 4.4 equals the negative log of H3O plus. Now again, if you've never learned logs before, you have no idea what to do with this step. So I'm going to show you this nice and big so you can see here. Okay, first of all, I took the negative and I moved it over here. And this is how you get rid of a log in an equation. You do on your calculator 10, and then it's it's caret. In the case of my calculator, it's this button, x to the y. And then I do have to type in the negative sign, 4.4. All right, so I get an answer of 4.0 times 10 to the negative fifth. Do we have to put it in scientific notation? No, but it's reasonable to. I wouldn't want you to write all those zeros. That would be a little bit unreasonable. So again, figure out this button on your calculator, this 10 caret button, and figure out how to find that. Last thing, oh, and of course this is an acid because it falls below base or below 7. Last thing I want to talk about today is this idea of acid strength. So I said down here you have like battery acid, okay, hydrochloric acid. Over here you have like oranges and stuff. We talked about baking soda and then of course sodium hydroxide. Well, there is something called strong acids and weak acids, and strong bases and weak bases. But that word in chemistry is a little funky, okay? The word strong in chemistry means that it completely dissociates in water, that it completely breaks apart. So there are 6 strong acids. This means that if these 6 strong acids, hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, chloric acid, if those are put in water, they will completely break apart into H plus and Cl minus. All right? The same thing goes for the bases. There are strong bases that will completely break apart. Basically, anything with an OH completely breaks apart when you put it in water. That means that they are very strong electrolytes. This is a picture of the light bulb being lit up really bright. Then, as you could probably guess, there are weak acids and weak bases. These do not ionize completely. They are a weak electrolyte, which is why this light bulb is not lit up as brightly. Here's some examples of some weak acids. There is acetic acid, which is vinegar. There's some other weak acids. Here's the one weak base that you'll talk about over and over again in AP. It's called ammonia. And you can see it looks different than the others because it doesn't have the OH on it. They are weak electrolytes. And the last thing I'm going to leave you with, just to totally confuse you, is there's strong acids and there's weak acids. And then within the weak acids, there are stronger weak acids and weaker weak acids. Okay? So as far as this scale goes, the next step is it can get a little bit more confusing.